Section 4-4 is on the derivatives of the other trig functions. And the objective of this section is, given a function that contains any of the 6 trig functions, find an equation for the derivative function. So if you recall, we've already seen what the derivative of sine and cosine are. We're now going to look at the derivatives of the other 4 trig functions: secant, cosecant, tangent, cotangent. All right. To start off with, though, let's take a little trip down memory lane here for us. If you recall, back in pre-calculus, you learned some properties of your trig functions, and we're going to use 2 of those sets of properties here. The first set of properties is what we called our reciprocal properties. And actually, there's a total of 6 of those. We're not going to look at all 6 of them. These are the 2 that we need to use. The first one is that cosecant of x is equal to 1 over the sine of x. And the second one is secant of x is equal to 1 over cosine of x. So notice in both cases here, I'm able to take the cosecant and the secant function, rewrite them as a quotient involving sine or cosine. And the reason for doing that, or the big hint here for us, is if I rewrite it that way, I know how to find the derivative of quotients, thanks to our topic that we covered in the last section. And I also know how to find the derivative of sine and cosine based on stuff we've covered back in Chapter 3. So there are the 2 properties we're going to use to help us find the derivatives of secant and cosecant. Now the other set of properties that we're going to work with are the quotient properties. And again, there's actually 4 of these properties. We aren't going to use all of them here, so I'm not going to worry about writing them all down. But in particular, the 2 that we need to rewrite tangent and cotangent. Tangent of x is equal to sine of x over cosine of x. And cotangent of x is equal to cosine of x over sine of x. So notice in both cases here, again, I'm able to rewrite tangent and cotangent in terms of a quotient of sine and cosine. And again, I know how to find the derivative of quotients. I know how to find the derivative of sine and cosine. I should be able to use these properties to help me find those derivatives. In fact, that's the technique we're going to use here, and that's what this little note says. We're going to use the quotient rule along with these reciprocal and quotient properties from trig functions to find the derivative of all 4 trig functions. Okay? Again, we already know 2 of them. We just need the last 4 trig functions to get all 6 trig functions. All right, so let's start out with derivative of tangent. So we're going to let f of x equal the tangent of x, which of course is equal to the sine of x over cosine of x. That's what we saw with our quotient property. And we want to find out what f prime of x is equal to. Okay? So let's see if we can go through and find the derivative of tangent. So f prime of x, and again, the way that I'm going to think about tangent of x is it's going to be sine over cosine. So I'm going to use quotient rule on that property there. So I'm going to think of it in this form right here as I take its derivative. All right, so it's a quotient, so follow quotient rule. Derivative of the top function, derivative of sine, is cosine of x, times the bottom function, which is cosine of x, minus the top function, which is the sine of x, times the derivative of the bottom function. Derivative of cosine is a negative sine of x. And that's all divided by the bottom squared, the cosine of x squared. That actually is the derivative of that function. However, we're going to kind of rewrite this so it's going to be in a form that's much easier for us to remember. And so in the numerator, I've got cosine times cosine, which is actually cosine squared. And then it's minus, but I've got this negative sign later on, so it's going to be plus here. Sine times sine is sine squared. And that's all divided by, again, the quantity cosine of x squared is the same as the cosine squared of x. That's just another way that we write that. Again, this is still a derivative, or a way we could write the derivative, but even better yet, I see in the numerator, that looks like one of our Pythagorean properties for trig functions. I know that sine squared plus cosine squared, or in this case, cosine squared plus sine squared, is equal to 1. So I can rewrite this as 1 over cosine squared. And still, that's a valid way to write the derivative, but even better yet, we're going to go one step further, because 1 over cosine Cosine is the reciprocal of secant, so 1 over cosine is just secant squared. So the derivative of tangent turns out it's equal to secant squared of x. All right, that's how we'll remember our derivative of tangent. All right, let's try another one of these. By the way, if you went through and found the derivative of cotangent, you'd find that you'd follow pretty much the same process that we just went through. So let's take a look at secant now. So again, we're going to say let f of x equal to secant of x, or using our reciprocal property, secant of x is equal to 1 over cosine. And we want to find out what f prime of x is equal to. All right. So again, I'm going to think of secant here in this reciprocal form. It's a quotient really, so I'm going to work with it, but I'm going to use quotient rule on that thing. Take the derivative of 1 over cosine of x. So the rule is, following quotient rule, derivative of the top function, derivative of 1 is 0, times the bottom function, cosine of x, minus the top function, 1, times the derivative of the bottom function, which is a negative sine of x. Derivative of cosine's negative sine. And that's all divided by the bottom squared again. So that's cosine of x quantity squared. And let's just rewrite this here slightly. So I've got a 0 times cosine. That basically is gone there. Those cancel out, obviously, 0 times anything. And then I've got a minus, and I've got a negative sign there. So that's going to become positive 1 times sine, or that's just sine of x in the numerator. And I'll write it as cosine squared of x in the denominator. Again, this is a way that you could remember the derivative of secant, but even better yet, we're going to write this in slightly a different form here. And in particular, I'm going to rewrite this as a product, actually. I'm going to write it this way. I'm going to think of sine over cosine squared. I'm going to take and rewrite that cosine squared there in another form and write it as 1 over the cosine of x times the sine of x over cosine of x. Of course, when I'm multiplying fractions like this, I just multiply the numerator together and then I multiply the denominators together. So I'd still have sine over cosine squared here. And again, I don't know if this is an easier form than the previous step, but the next step that I'm going to, it helps me see it by breaking it up this way. 1 over cosine, that's the reciprocal function for secant. So secant of x times sine over cosine is tangent of x. And that's the way we're going to remember the derivative of secant of x. Derivative of secant turns out to be secant times tangent. So derivative of tangent is secant squared. Derivative of secant is secant times tangent. And again, if you went through a similar process there with cosecant, you'd find you'd have a similar derivative. Not the same, obviously, but very similar. All right, so let's take a look at a few examples here of some derivatives for us. So example 1 there on page 143, they say to find differentiate y equals 3 times the tangent to the 5th of 7x. So the derivative, you've got a constant times a function. The 3 is your constant, and our rule is the constant stays out front times the derivative of our function. And again, if it helps you to rewrite this, you certainly could rewrite it. Maybe I should do that here for you. Go back a step and rewrite this. It's a composite function, and there's actually 3 functions that make up this composition. You've got the tangent of 7x, and then you're raising all that to the 5th power. That's what tangent to the 5th of 7x means. So we've got to follow chain rule to find this derivative. The 5th power is the outside function, so chain rule says take the derivative of the outside function, so the 5 comes out front, and we subtract 1 from the exponent to get 4. Chain rule then says to substitute in the inside function, which is the tangent of 7x. And then finally we multiply by the derivative of the inside, that is the derivative of tangent of 7x, but that's a composite function. So I use chain rule to find its derivative. So the derivative of tangent, we just found out, derivative of tangent is secant squared of something. That's the derivative of the outside function. Evaluate at the inside, that's the 7x, and then finally multiply by the derivative of that inside function. The derivative of the 7x there is 7. And again, when you get done with this using chain rule, you should be able to go through and count up the number of derivatives here. Those are the links of your chain, in essence. You took the derivative of the fifth power and got this guy right here. You took the derivative of tangent and got this guy right here. And then finally, you took the derivative of the 7x and got that 7 right there. Okay, so we have our correct number of derivatives there. And let's go ahead and simplify this then. 3 times 5 times 7. That's 15 times 7 there. That's going to be 105 times tangent to the fourth of 7x times secant squared of 7x. And there is our derivative. And there perhaps is some things you could do to rewrite that with tangent and secant, sometimes multiplying things like that. With trig functions, you could use your quotient or reciprocal properties to combine those in some way, but we're going to leave it right like that in that form there. If there's some obvious steps there, by all means, you could certainly do that. If it was tangent, for example, times cotangent, there's obvious things that would cancel, but we'll leave it right like that. All right, let's take a look at a few more examples there. The next one here, let's try secant. We took the derivative of secant, or found the derivative of secant a second ago. Let's see if we can find the derivative of this function here. They say to let f of x equal secant of x squared plus x. We want to find f prime of x. So again, you've got a composite function. Secant's the outside function. X squared plus x is your inside function. Follow chain rule. Chain rule says take the derivative of the outside function, derivative of secant. Derivative of secant, we just found out, was the secant of something times the tangent of something. This is why those parentheses are really helpful. Anywhere that you'd be writing down an x from your rule, put in parentheses there to indicate a placeholder for you that something goes there. And it's not going to be just x when you're following chain rule. So that's the derivative of the outside function. That's how I find the derivative of secant. I take the secant of something times the tangent of something. The second step of chain rule says to substitute in the inside function. So x squared plus x goes here, and x squared plus x goes here. That's a little bit new for us in the fact that there's two places that that inside function goes. And that's only because of the fact that our rule, the derivative of secant, involves two x's. Derivative of secant of x is the secant of x times the tangent of x. There's two x's in our derivative, so therefore there's two inside functions I'm writing down here. All right, that's the first two steps of chain rule. The third step of chain rule says now you multiply by the derivative of the inside. Derivative of x squared is 2x, and we add that to the derivative of x, which is 1. We're just following our rule for the derivative of a sum there. And there's really not much I would do with this one. You might put the 2x plus 1 out front, and that would be about it. Secant of x squared plus x times the tangent of x squared plus x. And I would leave it just like that. Derivative of that function is pretty straightforward there, but it's a little bit tricky in the fact that you end up with that inside function showing up twice because of the fact that the derivative of secant involves two x's in there. Secant of x and a tangent of x. All right, so then here are the derivatives of all 6 of our trig functions. And the book kind of splits these up into two columns here, and there's a reason for that. We'll talk about this in just a second. But let's focus on the ones over here on the left side first. So you have, first of all, the derivative of sine of x. Again, remember that's another way that we can write the derivative of a function, d dx of sine of x. That's the derivative of sine of x is equal to cosine of x. The derivative of tangent of x, turned out, we found out it was equal to secant squared of x. And finally, the derivative of secant of x turned out to be equal to the secant of x times tangent of x. So those are the 3 properties. We've used those now in a couple of examples. And we've proven those 2 derivatives there. Like I said, for the derivative of tangent and secant, if you went through a similar process, you would find the other 2 properties here for cotangent and cosecant. If you look over on the right now, we have the other 3 properties. Derivative of secant of derivative of cosine of x, of course, is equal to a negative sine of x. We've already used that one several times. In fact, we learned about that back in chapter 3. The second property there is the derivative of cotangent of x is a negative cosecant squared of x. And finally, the derivative there of cosecant of x is equal to a negative cosecant x cotangent of x. Now, if you look at how we rewrote these here, you'll notice that what I have in the left-hand column, sine, tangent, secant, and what I have over there in the right-hand column are their cofunctions, cosine, cotangent, cosecant. And you'll also notice that all the ones in the left column there, the derivatives are positive. There's no negative sign, I should say, out front, versus on the right-hand side, all those derivatives have a negative sign out front. So they're cofunctions, and they also have a negative sign. And furthermore, once I know actually the three rules that are over here on the left, I can use that property that I've pretty much just mentioned here about their cofunctions and that it's negative to help me come up with the other three that I have in the right-hand column. And the book kind of hints you towards this, and I will put that up here so you can see what the property is here. And then we'll go back and look at it. But it says, note, to find the derivatives of the cofunctions, just scroll that up a little bit so you can see the properties here along with this note. So to find the derivatives of the cofunctions in the right column, replace each trig function in the left column with its cofunction. So the first property there, you have the derivative of sine, and the derivative of sine, or I should say the cofunction of sine, would be cosine. The second property was for tangent. Instead of tangent, over on the right column, it's cotangent. And on the left, we have secant, and its cofunction is cosecant. So it says replace each trig function with its, in the left column with its cofunction. Not only do you replace the function you're taking the derivative of, but look at what's on the right side of the equal sign. So we have the derivative of sine is equal to cosine. If I replace each function in there with its cofunction, instead of the derivative of sine, it's the derivative of cosine, and instead of equaling cosine, it's equaling sine. I'm replacing each function in there with its cofunction. Take a look at tangent. Instead of derivative of tangent equals secant squared, replace those with their cofunctions. You get derivative of cotangent is cosecant squared. And same with the third property, you've got secant of x, derivative of secant of x is equal to secant of x times tangent of x. Replace each of those trig functions with their cofunctions. It becomes the derivative of cosecant is equal to a cosecant of x cotangent of x. So you're replacing each of those trig functions with their cofunction, and it says add a negative sign. And we already pointed that out, that all the results over there in the right column had a negative sign out in front versus the ones on the left did not. Okay, so you take the opposite of the result that you had, and you end up with those other three properties there. So if you know the first three over in the left column, you can use what you know there to help you come up with the other three. And I'd strongly recommend you do that. It's a nice way to help you remember all 6 of these. You really only have to know 3 of them, actually. And once you know those 3, you get the other 3 automatically with this property. All right, let's try a couple more examples now using these additional properties we've just added in there. So this one here says let f of x equal cotangent squared of 2x plus 1, and we want to find out what f prime of x is equal to. All right. Now again, if it helps, maybe I should actually do that. If it helps to rewrite the original function in another form, then go ahead and do so. I'm going to go ahead and do that here. You've got the cotangent of 2x plus 1, and that whole thing is squared. And I'm only doing that because so that you recognize we've got a composite function here, and which function is the outside function. The outside function is that squaring function, so that's where we're going to start. Chain rule says take the derivative of the outside function, which is going to be 2 times something to the first power. And chain rule says you substitute in the inside function. That's the cotangent of 2x plus 1. And then we multiply that by the derivative of the inside function. But the inside function, cotangent of 2x plus 1, is also a composite function. So follow chain rule to find its derivative. Start with the outside function in that. That is, start with the cotangent. Derivative of cotangent, we just learned. Again, here's the way that you should be thinking of this. I know the derivative of tangent is secant squared. So replace all of those trig functions there with its cofunction and take the opposite of that result. So instead of the derivative of tangent, it's cotangent. Instead of it equaling secant squared, it's a negative cosecant squared. So that's the thought process we have when we go to write this down. Derivative of cotangent then is a negative cosecant squared of something. And chain rule says you substitute in the inside function. That's the 2x plus 1. I guess I didn't need that parenthesis way over there. I'll just move him over. And then finally, chain rule says you now multiply by the derivative of the inside. Derivative of 2x plus 1 is just 2. And now let's just rewrite this here slightly. Let's take the negative and the 2 times 2. That's a negative 4 that comes out front. Cotangent of 2x plus 1 times cosecant squared of 2x plus 1. And we'll leave it right there in that form like that. All right, let's take a look at one last example here. One with cosecant. So again, we've got f of x is equal to the cosecant of x cubed minus x. And they want us to find f prime of x again. All right, again, if there's a way to rewrite the problem so you can see all your compositions, do so. In this case, I don't need to rewrite it. So let's just follow a rule. Anytime you're working with secant and cosecant, especially with chain rule, you got to be careful. It's going to be tempting to write down x's instead of those parentheses that I've used for many problems now to help you avoid this problem. But let's take a look at this one. Chain rule says to find the derivative of the outside function first, derivative of cosecant. Again, your thought process should be this. I know the derivative of secant is secant times tangent, so the derivative of cosecant is going to be a negative cosecant of something times cotangent of something. Instead of secant tangent, it's cosecant cotangent, and it is negative. And again, use parentheses there as placeholders. The second step of chain rule says you substitute in the inside function. X cubed minus x goes here, as well as right here. Again, that's new for us because we haven't seen that before, where we have to put that inside function down twice. So that's only because of the rule we're following. The rule has two x's in its rule, so therefore we have two inside functions to write down. That's the first two steps of chain rule. The third step of chain rule says to multiply by the derivative of the inside, derivative of x cubed minus x. It's actually a sum or a difference of functions here, so take the derivative of x cubed, that's 3x squared, minus the derivative of x, which is 1. And there is our derivative. And I'd probably rewrite this. I'll put the negative 3x squared minus, 3x squared minus 1 times the cosecant of x cubed minus x. My board just paused here on me. X cubed minus, minus the x times the cotangent of x cubed minus x. All right, and there is our derivative. And that, in fact, is the end of this section here for us.